continue with our discussion on non-stationarities, and then we will briefly talk on about ergodicity and kind of close our qualitative discussions and move on to more quantitative stuff where we will start looking at autocorrelation, autocovariance and autocorrelation functions. All right. So, what we were discussing yesterday is towards the end of yesterday's lecture is the trend type non-stationarities, and today we will talk about the integrating type non-stationarity. This is a stochastic kind of non-stationarity. If you compare this with a trend type non-stationarity, as I mentioned yesterday, trends by definition is a deterministic function of time. When nothing is mentioned and when you are said that a series contains a trend, it is kind of assumed that you are looking at a deterministic function of time, and of course, there is a stochastic component riding on top of it. And as you can see, and you have seen at least a couple of examples, there are many real life examples that fit into this framework. At every stage, you have to tell yourself that none of the models that we are building is actually a true representative of the process. I mean, it is not a true reflection of what is happening. What we are seeking are not correct models, what we are seeking are working models. If your model is able to explain the phenomenon, you develop more faith in that model, but then no, you do not get obsessed with that model and think that the model is a process itself. So, that is where you have to detach yourself. So, there is also a philosophy there, an attachment detachment philosophy. All right. So, coming to stochastic kind of trends, what do we mean by stochastic trend? Let me take you back here. Remember, we said when you have a trend type non-stationarity, x, that is your random signal, can be thought of as mu plus some stochastic signal. Now, this mu, if it is a deterministic function of time, you have a trend type non-stationarity. Now, your mu is not a deterministic function of time, it is a stochastic function. I mean, I do not say stochastic function, it is coming out of a stochastic process, and there are obviously many possibilities now. We are interested in one particular type of stochastic trend, and this is the integrating type non-stationarity. There are different names to this, and as we call this as integrating type in physics or in statistics also, this is known as random walk phenomenon. Then you have Brownian motion and so on, named after the botanist Brown. So, if you look at the history of Brownian motion, you will find that Brown had actually discovered this phenomenon in his field. He was observing the movement of pollen, but of course, he did not get into any math, right, because perhaps he did not have the time or he was not interested and so on. Maybe he was, but it was not meant to be that way. It is nearly a century later that Einstein stumbled upon this kind of phenomena and then gave a more quantitative, statistical, very rigorous explanation to this kind of phenomena, and that is when the name of Brownian motion came along. And in all of this, it was called random walk. I am sure you understand what is random walk. I am standing here. Now, the random walk phenomenon is as follows. I am standing here. Now, I have to decide whether to go to the left or to the right. And if there is equal probability, that is one kind of suppose I toss a coin, a head turns up, I move to my right, and a tail turns up, I move to the left. And that if it is a fair coin, then it is going to be equal probability, and I am going to do this at every step, right. So, I toss a coin, let us say tail shows up, I move to my left, then again I toss a coin, then the same story. So, this is an example of a random walk phenomenon, and such kind of phenomena are not fictitious, in the sense it is not some kind of a very abstract phenomenon. As I said, starting with the observation of Brown, people have observed that several phenomena in nature and even kind of man-made follow kind of a random walk phenomenon, and we are interested in one particular class of random walk phenomena, which is the integrating type. Now, why is it called the integrating type? Of course, I have an equation for you here, but this equation would not make much sense at this moment to you until I define what is white noise. The Ek that you see in the equation is nothing but the white noise signal. That would not make too much sense for you until we define autocovariance function and then define white noise. We will see later on that this integrating type process is also an autoregressive process of order 1, right. So, at the moment, leaving aside the definition of Ek, think of just accept that to be white noise. If you look at the definition, say n runs from 0 to k. So, that is the definition of white noise here. There is a mistake there in the equation. I will correct it. It should the index, dummy index should be n. Okay, that is fine. It is a minor one, we will correct it. What is happening is, think of this white noise as of now qualitatively as a shock wave that is unpredictable, and you can see that the current state of the process is an accumulation of all the shock waves right from the beginning. In fact, strictly speaking, I should be writing here minus infinity, but for now we will assume that the beginning is indexed at 0. So, because of the accumulation of the shock waves at any instant in time, what you are essentially doing is integrating them, and that is why the name integrating effect. Of course, it is not so obvious why this is a random walk phenomenon. The random walk nature comes about much more clearly when we write what is known as a difference form of this equation, and slowly you should start getting used to this, a difference form equation, a convolution equation and so on. This is said to be in somewhat convolution form. How do you write the differenced version of this? Xk, yeah. Let us write the backward difference, minus xk minus 1 equals Ek, very good. All right, this we call as a difference version, and this version of the that is this equation representation for the integrating type process is a lot more useful. We work with this equation much more often than this. Sometimes we use this for theoretical analysis. In fact, now we can rewrite this as xk equals xk minus 1 plus Ek. Now, you can see some kind of a random walk phenomenon coming out. If you are standing at k minus 1, the next state is the previous one plus some random component, which is an unpredictable one, adding up, and that is why the name random walk comes about to this process. Of course, there are different types of random walk phenomenon, but this is simplest, and as I told you, this is also called the integrating type process. Now, this is an autoregressive process also, because the process is regressing onto itself. You should get used to this term autoregressive, and of course, we will talk about that more in detail later on. Xk, if you look at the process, xk minus 1 is actually regressing onto xk. Regression is a term that comes from hypnotherapy and so on, where you are looking at effects of past regressing onto the present. There are quite a few movies based on that, right. We will not get into that now. Anyway, so you can see that essentially this is a random walk phenomenon, and another way of looking at this integrating type process is from a prediction viewpoint. Given all the information up to k minus 1, the best prediction of an integrating type process is the previous value itself. Why did I write this way? By the way, you should slowly get used to this notation. X hat of k given k minus 1 implies that I am predicting x at k given all the information up to k minus 1, not just at k minus 1, okay. And that happens to be xk minus 1. Why is that so qualitatively? Sorry? Predict the? Correct. So, because Ek is unpredictable by definition. What we mean by unpredictable? Given any amount of history of Ek, the prediction of Ek is the mean itself. Typically, these Eks are assumed to be 0 mean. So, the best prediction is the previous value itself. Now, what is the non-stationary part of this? We have not seen why it is called non-stationary. We will prove this a bit later on when we learn how to analyze the autoregressive processes, we can prove it one way. The other way that you can see right now, instead of getting into the autoregressive world, there is a way to prove that this is non-stationary. How do you prove that it is non-stationary? Typically, what is a procedure that we adopt? We will try to see if the mean is changing with time. What happens to the mean of this process? So, if this is the equation, we can use this equation to arrive at the mean. What would be the expectation? 0, right? Because expectation operator is a linear operator. On the right hand side, the expectation yields a value of 0. So, that is not an issue, it is stationary in the mean. What about the variance? How do you calculate the variance? Why? Where is central limit theorem coming into it?
It's a sum of n random.
Central limit theorem is only used to arrive at the distribution. Okay, I mean a part of also that tells you what is the variance, but the focus of the central limit theorem is to give you results on the distribution part. Simple, xk is made up of k random variables, right? Sum of k random variables. How do you compute the variance of sum of random variables? Sorry? Suppose I have, let's take a simple example. Suppose I have two variables y1 and y2, and x is made up of x is essentially y1 plus y2, two variables y1 and y2, and I add up to produce x. What is the variance of x?
Variance of y plus variance of y minus covariance of y1
Minus, why minus? So, sigma square y1 plus sigma square y2 2 times, very good, 2 times covariance between y1 and y2. Now, you can extend this equation to n variables or k variables. Apply this to find out the variance of xk. Sorry? K times sigma square e. Why? What happened to the covariance? Why? What?
They are independent. E's are independent.
Did I say independent? At the moment it is uncorrelated. Okay. There is, of course, we will talk about two different processes, white noise and IID. The covariance terms vanish by definition of the white noise. Remember, our white noise sequence is such that it is unpredictable. What do we mean by that? Unpredictable in a linear sense. Let me make that complete statement. And because it is unpredictable in a linear sense, there is no linear dependency between any two observations, or at any two instants the signal is uncorrelated, which means all the cross terms would vanish, and therefore, we would be left with, so sigma square xk. Remember, strictly speaking, we are supposed to use the random variable, but as I said, we will slowly dilute that notation and work with sigma square here. Xk will be used for both observation as well as a random variable. K times sigma square e, if sigma square e is the variance. We will give a formal definition of white noise shortly. Ek is assumed to be stationary by definition. Now, can we conclude that xk is non-stationary, right? Because the variance is changing with time. That is good enough to tell us that it is non-stationary. We will arrive at another, we will arrive at the same conclusion by looking at the poles, so called poles of the autoregressive model, but we will reserve that for a later discussion. Good. So, at any signal, at any instant, sorry, the signal is accumulation of all the shock waves, and therefore, it is called integrating effects. This is something that we have already discussed. Let us get a feel of how this such a process looks like. I am showing you just one realization of an integrating process. You can easily simulate integrating processes even in R, you can generate these realizations. I will show you later on how to simulate integrating processes, or even in general ARMA and ARIMA processes, maybe a couple of lectures down the line. So, the main point here is going back to this difference equation form. We have written it this way to see that it is a random walk process, Now, we will go back to the previous equation that we had to see that a single degree of differencing can produce a stationary series. That is, xk is non-stationary, E is stationary, and lot of the theory that we are going to work with is applicable to stationary random processes. Now, what this equation tells me is by differencing x once, I am able to produce a stationary series, right. This is a pure integrating process, therefore, 1 degree of differencing has actually produced a white noise. And on the plot you see this, on the top I show the realization of the integrating process, and at the on the bottom in the bottom panel you see the differenced series, and at least visually when you look at it, it appears to be stationary, whereas the top one appears to be non-stationary. Although you should be careful when you draw conclusions visually, it is lot more easier to detect trend type non-stationarities visually than the stochastic ones. For the stochastic ones, in particularly the integrating type and so on, one has to formally conduct a statistical test, and we will talk about this so called unit root tests. What we mean by unit root here is, when you go back to the difference equation form or the recursive equation form, you see that the difference equation form has a root at 1 at unity. Yes.
E has constant variance even.
Right. E has
Constant variance, or it's a variable variance?
Yeah, it is stationary. The moment it is stationary, that means the variance has to be constant. So, by definition, white noise is a stationary uncorrelated process, and we have already made use of the uncorrelated property in deriving the variance of xk. And when I wrote this expression, at that point I said E, we have invoked the stationarity property of Ek. Somewhere we have to fix things. So, we assume that this white noise is stationary. You can have non-stationary white noises also, but for now we will work with stationary white noise, and that is what gives us this expression. Okay. All right. So, there are these unit root tests which will allow us to determine whether the process has a random walk behavior, I mean integrating type behavior or not. Now, many a times two things can happen, that is, here it is a very simple case where I difference once and I recover the white noise. In a more general sense, you may have to difference many times to make the process stationary. We do not know. Typically, you will not encounter the case where you have to difference more than 3 or 4 times and so on, but one may run into such a situation, and this degree of differencing has to be determined on a case by case basis. Here, single degree of differencing has produced a white noise. That is point number 1. Point number 2, it is, you should not think that always this, when this integrating type non-stationarities are present, the moment I difference or how many ever times I difference, I will get a white noise process. It is not necessarily the case. The statement says that once you difference, or maybe d times you difference, you will recover a stationary process. In other words, instead of Ek, you could have here some Wk, where Wk is a stationary process. In which case Wk itself has some kind of a model to be built, and put together we call this as an ARIMA process, but the terminology will become clearer later on. When single degree of differencing produces white noise, we call this as a pure integrating process. That is it, it is called an integrating process. When a single degree of differencing or any d degree of differencing produces a stationary process which is not necessarily white noise, then we run into what are known as ARIMA kind of processes, which we will talk about later on. Now, are there processes out there which have this kind of a behavior? Numerous. You will find them predominantly in econometrics. A lot of stock prices, stock market prices, financial variables and so on have this kind of a behavior, and a lot of disturbances that you see in engineering processes also have a random walk kind of behavior. We will shortly understand through the help of autocovariance function a different aspect of this random walk phenomenon in terms of the correlation and so on. But we will restrict ourselves to this integrating type processes when it comes to stochastic non-stationary, stochastic trends. So, there are two kinds of non-stationarities that we will think of, in fact 3 I should say, including the periodic one. One is the deterministic one, which subsumes the polynomial trends as well as periodic ones. In that sense we are only looking at 2, but if you separate the periodic one, because we will give a separate treatment to the periodic one, then we have the stochastic type trends or non-stationarities, in which we will consider particularly the integrating type only. These two are enough to trouble us in this course. To begin with, we will restrict, will confine our discussions to stationary processes. Once we are in a position to model stationary processes, then we will bring up the non-stationary part. For example, here I said instead of E, you could have W, where W is a stationary process. Let us say you discovered by a single degree of differencing that you have a stationary process. For example, in this figure that you see, the top comes out of an integrating process. You would not know whether it is a pure integrating process or an ARIMA kind of process. A single degree of differencing gives you a stationary series like the one that you see in the bottom here. Now, obviously, by looking at this, you would not be able to say if it is a white noise, if it is a realization of a white noise process. Can you? It is not possible, right, and that is going to be the subject of discussion very soon, where we will study autocovariance functions, which will tell us whether this is a realization of a white noise process or not, correct. It would be great if you can look at the series and determine straight away that it is white noise, then the entire theory would crumble. Life is not so easy.
Why is it particularly a difference? Is there, can we have summation or anything else?
What?
Do we have particularly difference and difference?
No, the origin is this, okay, or some people argue that the origin is this. It is a good question. The difference equation comes because of the random walk kind of phenomenon. So, I am at this state, right, or this is xk minus 1. What would be xk? A random component adding on to the present position, present state, whether I move to the left or right. Remember, ek can take both positive and negative values in general, and there is a probability associated with that. So, all we are saying is the next position is the current position plus some random component, and that is why you can begin with this equation if you like, and if the probability, that is the phenomenon that is determining my next position, is a white noise kind of thing, then you have a pure integrating process. If the phenomenon that is going to govern my next position, that is where I move from k minus 1, itself comes out of some stationary process, which is also a probabilistic process, then we have a more general ARIMA kind of process. So, the starting point for an integrating process can be different, in the sense I could start with this is what we have started with, claiming that it is integrating process, but someone else could say no, I will assume that my starting point is this equation, because this allows me to explain the random walk phenomenon, and then show that this is an alternative description. So, there are several ways of describing the same process. This is something that you should slowly get used to. Any process in general will have different forms of descriptions or representations. They all mean the same. It is just that the mathematical equation looks different, and which mathematical equation do we want to work with? In other words, which model or representation we want to work with entirely depends on the application that we are looking at and the context that we are looking at. In this case, we began with this, and then this kind of summation equation, and went on to the difference equation. I might have as well begun with this and gone to this form as well. Okay. So, to answer your question, the difference equation form comes about by virtue of the nature of random walk, its current position plus some random quantity. Okay. So, let us actually now close the discussion with a small cautionary note on differencing. This differencing is a very attractive option to get rid of the integrating type non-stationarity or to model the integrating type non-stationarity. But many a times you may end up differencing when there is no need to do so. That means your process is not an integrating type and you may still end up differencing the series, maybe inadvertently or accidentally or whatever, or it is an oversight. That can actually cause more harm than good. So, one has to be careful, you have to be sure that there has to be enough conviction to believe, in other words, to difference a series. For example, let me give you a very simple example. Suppose the given series was Ek itself. In the simplest case, I gave you a realization of white noise. You did not let us say bother to look at the series, to visually inspect the realization or even conduct the basic tests. You simply said, okay, no, I have been taught that the first step is differencing the series, and let us see if it makes a difference. Okay. So, you ended up differencing this series, and let us say you produce a new series, let us call it as V, which is a result of differencing this white noise. What have we done here? The original series is coming out of a white noise process, right? That means there is no model to be built. Now, differencing has actually introduced some kind of a correlation, right? You can actually take two successive observations of Vk and you will find they are correlated. If I were to write the expression for V of k minus 1 or even k plus 1, you will see the same thing. So, this is the expression for V of k minus 1. You can see that there is a correlation between Vk and Vk minus 1, likewise Vk and Vk plus 1. This is artificially introduced by virtue of differencing, and we will see later on that this can cause problems. As is, you can see qualitatively you have introduced by accidentally differencing the series a spurious correlation, and you say, no, yeah, now I have a series that is correlated, I will build a model. If that is the joy that you want, you can go ahead and do it. Even if I give a white noise process, you want to build a model, you are so desperate, then you difference the series and then build a model and say this is the model, and then you again go back to your original series. Ultimately, remember, you have to forecast this series that has been given to you. You may build a model for V and then come up with a forecast equation. All of that is not necessary at all. Had you followed a systematic procedure, you would not have actually run into this unnecessary differencing. In system identification, which we do not study here, unnecessary differencing can actually amplify the noise effects in the measurement. We will not go into that. So, there are precautionary measures that you have to take. You have to exercise some restraint when it comes to differencing. Just do not keep on differencing. It is like, beating until the series speaks to you. Do not thrash it up. Okay. It is going to have its own repercussions. We will come to all of this again when we look into study ARIMA models.